All right, the second example we're going to look at here is a little more practical. Let's say you have a biological secretion that's made up of proteins that are hardened into a simple cubic arrangement. In other words, they've arranged themselves to form a giant cube. If you can measure the density of this secretion and you know the molecular mass of the secretion, one thing that you might be asked to find is how far are these proteins apart from one another. And this is a rather relevant problem because depending on how far apart they are from each other, it's going to tell you some things about how they can interact with one another, right? What kind of maybe large macrostructure they've created. So you've been provided with all these things on the left-hand side. However, what I will tell you is the very first thing that you're going to want to do whenever you're looking for a physical characteristic of this is you've been provided with the mass per mole. What you're probably going to always want to do is find the mass for each individual particle. So here you have 50 kilograms per mole. A mole is just an arbitrary number. So what you can do is you can just replace that division by a mole with a division by an arbitrary number. Right? And when you divide this out, what this will tell you is it will provide you with literally how much each individual particle weighs. Right? This lets you look at it in a microscopic fashion. So if you divide these out, you'll get the mass of each one of these proteins in kilograms. Now, this is rather useful due to the fact that if we are looking for a physical measurement here for how far the proteins are apart, we can usually, given that we know they're in a cube, relate the distance things are apart to the volume of a cube. And the volume of the cube is directly relatable to n here, the number density. So what you can do here is, given that we know that the density of the thing is 750 kilograms per cubic meter, we know the mass per particle is 3.303 times 10 to the negative 23 kilograms. We can actually find the number of these proteins that will fit into a particular unit of volume. So you can just basically divide these out, and what you will get is, for these proteins, you will have quite a large number of them that fit inside a cubic meter. Right? So you'll get about 10 to the 24 of them that fit inside a cubic meter. Now, you might ask, well, how does this help me do anything? Well, at the end of the day, if I know how many of them fit inside a cubic meter, I can actually find the volume that each individual one takes up by simply taking 1 over the number density. And typically speaking, since the number density is the number per unit volume, if you flip this around, you will get how much volume each one takes up. So if you take 1 and you divide it by 9.033 times 10 to the 24, this will give you the volume of each particle in cubic meters. And that'll be roughly how much space each one takes up. It comes out to 1.107 times 10 to the negative 25 cubic meters. Now, this seems like a real small number, but proteins are pretty small, and a cubic meter is actually very, very large. It's a decent chunk of volume. Now, once we've done all this, we do have the volume that each particle takes up, which is going to be directly related to the radius that we're looking for. The question is, well, how are they related? Well, the idea here is you actually have a cube. So the volume of each little cubic section that you're dealing with is going to be roughly equal to the radius of each one of those little tiny cubic sections cubed. Right? Length times width times height. If they're all the same, you're going to just cube it. Right? Specifically, right, if you want to see how this works, right, let's say we have, one little particle here and another little particle here and then like a third one over here. If we put each one of them into a little cubic box, right, of a volume. Sorry, it's taking me forever to draw this. You'll notice that the length or the radius of one of the individual box sizes, so from here to here, is roughly the same as the distance in between the particles if they're evenly spaced. What that means is we can find R very quickly because we know what V is, and then we know what R is. You can simply take the cubed root of V, and you will get the distance in between each particle, which is 4.801 times 10 to the negative 9 meters, or 4.8 roughly nanometers in between. So using this, you can actually figure out exactly how far proteins are apart if you know their crystal structure and how much mass they take, or how much each one of them weighs, and how much density they have. It's directly relatable to physical characteristics. The reason why we don't use concentration in moles is because if you had moles present here, making this transition from number density or concentration in terms of number of particles per cubic meter to the volume per particle is very hard because you would have the mole left over in this step. And that's why we typically remove it, right? As of last year, I think, the mole literally is now just an arbitrary number. So you're better off just, popping it out of most of your problems.